Okay. Now the students, then we will see chapter 4. Frequency responses. In that, one topic is called as BOD plan. Okay. Now I just give the few basics of this. Now previously we just do the time domain analysis, which include the transient state analysis as well as steady state analysis. Transient state analysis as well as steady state analysis, right? Time response of first order, time response of second order, then we will see all these things. Now when we go to the root locus diagram, then we will just draw the movement of the closed loop poles now in the S plane. Now that is a time domain analysis or frequency domain analysis, and most of the are thinking that that is a frequency domain analysis because that is S plane. No. Now if you replace S is equal to j omega, means assume the real part is 0. If you replace S equal to j omega, pure frequency response, pure frequency axis, then only it will call it as a frequency responses and frequency domain analysis. But in a root locus, we are not replacing S with j omega, we are replacing S with sigma plus j omega. So that is not a pure frequency domain analysis. The pure frequency responses or a pure frequency domain analysis comes under the frequency domain analysis or frequency response of the control system is of three types. One is BOD plot, another one is polar plot, and another one is Nyquist plot. These are the three frequency response of the systems, or these are the three frequency domain analysis. Now I just tell you only one point here. All these three plots are the frequency response of, all these three plots are frequency response of open loop control system. All these three plots are the frequency response of open loop control system. All these three plots are the frequency response of open loop control system. Now that's what I am saying from the first topic of root locus onwards. All the plots, now the total topics in the subject, we are taking only a open loop transfer function, but everywhere we want to do the analysis of closed loop control system. So all these plots are the frequency response of the open loop transfer function. From these plots, then we will do the analysis or stability analysis or stability of closed loop control system. So even if you take the open loop transfer function, but ultimately finally we want to do the analysis or stability of closed loop control system, which means that now I want to find the stability from the BOD plot, I want to find the stability from the polar plot, I want to find the stability from the Nyquist plot, but all these three plots are the frequency response of open loop transfer function. Understand or not? Now this is the frequency response. Now in that, then we'll take a first topic as a BOD plot. Okay, after that polar plot, after that Nyquist plot, we'll see. Now this is very important, students. Okay, this is very important. Now how we are doing the responses with respect to time. Now we will see the responses with respect to frequency is called as a frequency response, but that response you are taking only for the open loop transfer function. Now based on the response, then we will do the analysis of the closed loop control system. Clear or not? Okay. Now, sir, what is BOD plot, sir? Now what is polar plot, sir? What is Nyquist plot? I am already giving the definition. The BOD plot is the frequency response of open loop transfer function. Okay. Now I just give a few points of the BOD plot, but before that you just take a copy of this. Now, a few points I want to say. Now, what is BOD plot? What I'm saying, this BOD plot, this is the BOD plot, which is the frequency response of, this is the BOD plot, this is the BOD plot, which is the frequency response of open loop transfer function. And second point, in BOD plot, the x-axis is, in BOD plot, the x-axis is a logarithmic frequencies. In BOD plot, the x-axis is not a frequency, the x-axis is a logarithmic frequency. Therefore, BOD plot is also called as BOD plot is also called as BOD plot. In BOD plot, the x-axis is a logarithmic frequency. Therefore, BOD plot is also called as logarithmic plot. Now, where x-axis is a logarithmic plot, which means, now where x-axis is a logarithmic frequencies, now that particular graph is called as semi-log sheet. The BOD plot is drawn on a semi-log sheet. In the semi-log sheet, actually the x-axis is logarithmic frequencies. Okay. Now just take these points. So this is the introduction of this BOD plot. Now the students are having some doubt that, now what is the logarithmic frequency? Now this is the logarithmic frequency. Now logarithmic frequency means, what about base? This is logarithmic frequency. What about the base? Logarithmic frequency. Now the base is, now this is the logarithmic frequency. Now the base. Now see here, this is the frequencies. If the frequencies is like this, 1, 10, 100, 1000, 10,000, like this. Now if you see here, 1 into 10, 10, 10 into 10, 100, 100 into 10, 1000, 1000 into 10, 10,000. Now, if the frequencies are changing by a factor of 10, if the frequencies are changing by a factor of 10, is called as decade. Very, very important. If the frequencies are changing by a factor of 10, is called as decade. So we generally taking a frequencies by a factor of 10, therefore it is called as decade. Therefore you just generally take it as logarithmic frequency and base is 10. If the frequency is changing by a factor of 10 is called as decade. Here I will write, okay. Frequency is changing by a factor of 10 is called as the frequency changing by a factor of 10 is called as decade. If the frequency is changing by a factor of 10 is called as decade. Now see here, the number of decades between any two frequencies, the number of decades between any two frequencies is log highest frequency base 10 minus log lowest frequency base 10. So we generally take a frequencies by factor of 10 only. So the number of decades between any two frequencies is nothing but highest frequency is 10 power 4 minus lowest frequency is 1, 4 log 1 is nothing but 0, 4. So how many decades? 1, 2, 3, 4. Like that you can find the decades between any two frequencies. We generally taking a frequencies by a factor of 10 itself. Okay. So generally we are assuming logarithmic frequency because this is a semi-log sheet. Then that log omega base is you treated as 10, which means that in turn the frequency is changing by a factor of 10 itself. Okay. Now in the similar kind, now the frequency is like this. Now the frequency, if you see here the frequency is 1 into 2, 2, 2 into 2, 4, 4 into 2, 8, 8 into 2, 16, 16 into 2, 32. Here the frequency is changing by a factor of 2. Here the frequency is changing by a factor of 2 is called as octave. If the frequency is changing by a factor of 2 is called as, if the frequency is changing by a factor of 2 is called as octave. Now octave, then what about the base? Now this is base. Now log omega base is 2. If the frequency is changing by a factor of 2 is called as octave, right? Now see here, in the same thing here also you can find the number of octaves between any two frequencies is nothing but log highest frequency base 2 minus log lowest frequency base 2. Now highest frequency is 32, 2 power 5 minus lowest frequency is 1, 0. So total 5 minus 0, 5 octaves, 1, 2, 3, 4, 5. Like that you can find the octaves and decades between any two frequencies. Generally we are taking in terms of decade. If the question is in terms of octave, then you can think that the frequency is changing by a factor of 2. Okay. Otherwise by default we can go for decades only. Okay. Note on this. Okay. So these are the few important points while we start drawing the Bode plot. Okay. So you have to identify that x-axis is not a frequency axis. X-axis is a logarithmic frequencies. And this Bode plot is actually of two plots. One is Bode magnitude plot. Another one is Bode phase plot. One is Bode magnitude plot, another one is Bode phase plot. So this Bode magnitude plot is nothing but, now this is the logarithmic frequencies. Now this is magnitude, the magnitude of open loop transfer function. But this is the magnitude of open loop transfer functions in terms of dBs. This is in terms of dB. Now, this is phase angle of open loop transfer function. This is logarithmic frequency. Now, this is phi, the phase angle of open loop transfer function in terms of degrees. The phase angle of open loop transfer function in terms of degrees, the magnitude of open loop transfer function in terms of dB. This is Bode magnitude plot and that is Bode phase plot. Now, so Bode plot is nothing but the Bode magnitude plot, but we will draw the Bode phase plot also. But one point you have to identify that if you want to draw the magnitude plot, now magnitude in terms of dBs versus frequency, phase angle in terms of degrees versus frequency is the Bode phase plot. So I think you know how to calculate the magnitudes and you know how to calculate the phase angles. So the drawing the Bode plot, and which is a very simple one. Okay. Now we will try to directly draw the Bode plots because we are very familiar of finding the angles and phase magnitudes. So if you are very good at calculation of angles and phases, then the Bode plot is a very simple plot. So now I'll take one small problem, and this is G of S, which is equal to S. 1, 0 is at origin. So 1, 0 at origin. Now I'm trying to draw the Bode plot. Now replace S equal to j omega. Then only this is called as a pure frequency response or frequency domain analysis. 0 plus j omega. Now the magnitude is magnitude of g of j omega, which is equal to square root of a square plus b square. Therefore, this is magnitude omega. I want magnitude in terms of dB. I want magnitude in terms of dB, which is equal to 20 log omega base 10. Generally, we are taking frequency by a factor of 10. Now, this is a magnitude in terms of dB. Now, if you observe here, this is the frequency response characteristics, frequency response of the open loop transfer function. Now, your magnitude is depends upon frequency. Now, this magnitude is depends on frequency. Then the problem starts. So, when the magnitude is depends upon frequency, now practically how many frequencies are existing? If you consider all the positive frequencies from 0 to infinity, then omega 0, omega 1, omega 2, omega 3, omega 4, omega 5, like that, infinity frequencies are available and infinity magnitudes are calculated. So it is possible practically? No. So this magnitude is depends upon frequencies. It is not possible to calculate all the magnitudes by substituting all the frequencies. That's why in Bode plot, instead of this magnitude calculations, we will go for a slope calculations. Okay, the slope is nothing but a constant rate, change in y-axis by change in x-axis. Instead of this magnitude calculations, then we go for the slope calculations in all the Bode plot. What is the slope? What is the slope of the Bode plot? You just see here. What is the slope? Slope is nothing but change in y-axis. What is change in y-axis? Magnitude m by change in x-axis. What is x-axis? Logarithmic frequencies. Units are also important. Now y-axis is dB per x-axis logarithmic frequencies, but frequencies changing by a factor of 10. Therefore, this is called as decade. dB per decade. Now, therefore, this is m2 minus m1 change in y-axis by change in x-axis log omega 2 minus log omega 1. So frequency is changing by a factor of 10. So change in y-axis by change in x-axis is called as slope. Now this is the slope of the Bode magnitude plot. Now we will see now what is the slope. Now the slope calculations are very simple. Now the slope, which is nothing but, now see here, slope dm by d log omega. Now plus 20 is constant. Log omega differentiate with log omega is 1, which is dB per. Frequency is changing by a factor of 10. Therefore, this is called as dB per decade. Now this is the logarithmic frequency. Now this is the Bode magnitude plot in terms of dB. Now this is the positive slope or a rising slope. Now this is the rising slope, positive slope. Now this positive slope is nothing but plus 20 dB per decade. Now this is the positive slope, which is the rising slope, which is plus 20 dB per decade. Clear or not? Now this is the positive slope, which is the rising slope. Now this is the slope of this is the Bode plot of 108 origin. This is the Bode plot of 108 origin. Sir, where we want to start, sir? Now that starting point we will calculate. Now that is the starting magnitude, where it will start on y-axis, that we will see later. Okay, we will calculate what is the starting magnitude, how to find the starting magnitude, and what is the procedure also we will see. Just for easy explanation, I will write I will start somewhere and I will write the slope is plus 20 dB per decade. Now see here. Now that is the Bode magnitude plot. Now the slope calculations are very simple. That's why in all the Bode magnitude plot calculations we go for slope instead of magnitude, because it is difficult. Okay. Now what is Bode phase plot? Now we will see the Bode phase plot also at a time. But before that, you just take a copy of this. Okay. Now we'll see the Bode phase plot also. Okay, because that is phase angle in terms of degrees. Now this is g of s, which is equal to s, 1 0 at origin. Now replace s equal to j omega. If you replace s equal to j omega, 0 plus j omega. Now the phase angle of g of j omega, which is equal to numerator plus tan inverse imaginary part by real part, which is equal to plus tan inverse infinity, which is equal to plus 90 degrees. Now this is tan inverse infinity, which is equal to plus 90 degrees, which is independent of frequency, which is independent of frequency. When it is independent, then it is our job is very easy, right? Now the phase angle in terms of degrees, the phase angle in terms of degrees versus frequencies. Now this is 0 degrees. Now this is 0 dB. Now this is 0 dB. Now this is 0 degrees. Now which is independent of frequency, plus 90 degrees. Plus 90 degrees, which is constant and which is independent of frequency. Plus 90 degrees, which is constant and which is independent of frequency. The phase angle is plus 90 degrees, which is constant. This is positive phase, this is negative phase, this is positive slope, rising slope. Okay. Now this is plus 90 degrees, which is independent of frequency. This is BOD phase plot of 1 0 at origin. This is BOD magnitude plot of 1 0 at origin. Then one simple point I am asking. Now see here. This is 1 pole at origin, sorry, this is 1 0 at origin, 1 0 at origin. Therefore, slope is plus 20 dB per decay. Now, if I am asking, this is 2 zeros at origin, square, omega square. Omega square means it will come to 2 into 20. Understand not? 2 into 20. Now, if it is cube, 3 zeros at origin, cube, 3 into. So what we can understand here, now g of s, which is equal to s power n, which is nothing but n zeros at origin, which is nothing but, if it is n zeros at origin, g of s, which is equal to s power n zeros at origin, which is equal to slope which is n into plus 20 dB per decay. Is it right or not? 1 0 at origin, slope is 1 into 20 dB per decay. 2 zeros at origin, 2 into plus 20 dB per decay. 3 zeros at origin, 3 into plus 20 dB per decay. Now similarly the phase, 1 0 at origin phase is 1 into 90 degrees, independent. 2 zeros at origin, 2 into plus 90 degrees, independent. 3 zeros at origin, 3 into plus 90 degrees, independent. Therefore, now what is the phase? Phase is n into plus 90 degrees, which is independent of frequency. This is the table of phase and slope of n0 at origin. Okay. This is now your problem may be 1 0 at origin or 2 0 at origin or 3 0 at origin, or you can easily solve. Okay. First you note down this. Okay. Now in the same manner, this is zero set origin. Can we go for pole set origin? Then what should be the changes? G of S, which is equal to 1 by S, one pole at origin. Now replace j omega, 0 plus j omega. Now the magnitude is 1 divided by square root of real part square plus imaginary part square, 1 by omega, omega power minus 1, which is nothing but minus 20 log omega base 10. Therefore slope, which is nothing but, because this is the depends upon frequency, right? Now this is depends on frequency. Therefore this is nothing but minus 20 log omega is base 1, which is nothing but minus 20 dB per decay. This is a falling slope, negative slope. Therefore I am already saying that where the Bode plot start, that we want to calculate later, that is called as starting magnitude. Here it will start, here that we will find. Now this is the falling slope, negative slope. Now this is minus 20 dB per decay. Now previously there is a rising slope. Now this is one pole at origin. Now similarly, what about the phase? One pole at origin, 1 by S, 1 by. So phase angle is denominator, therefore minus tan inverse imaginary part by real part, which is equal to minus tan inverse infinity, which is equal to minus 90 degrees. Now this is the phase angle minus 90 degrees, which is independent of frequency, which is independent of frequency. Now the phase angle which is minus 90 degrees, which is independent of frequency. Now this is 0 degrees. Now this is minus 90 degrees, which is constant and which is independent of frequency. This is minus degrees, which is constant and which is independent of frequency. Am I not? Now you tell me, now in the same manner what I am saying is, one pole at origin, slope is minus 20 dB per decay, because this is s power 1. If it is s square, 1 by s square, two poles at origin, omega power minus 2. So this is omega power minus 2. Therefore 2 into minus 20. Am I not? Actually this is minus 2 into 20. Then I can write 2 into minus 20. Right? So 2 into minus 20 is nothing but how much? Minus 40. Now similarly 1 by s square whole square. So denominator minus 2 into minus 90 degrees. Which means that one pole at origin slope is minus 20. One pole at origin phase is minus 90 degrees. Now 2 is nothing but multiplication. 3 is nothing but multiplication of that. So can I write like this? Now G of S, which is equal to 1 by S power n. If G of S which is equal to 1 by S power n, this is n poles at origin. If there is n poles at origin, then what is the slope? If it is n poles at origin, the slope is n into minus 20 dB per decay. Phase is n into minus 90 degrees, which is independent of frequency. Now this is the another table which consisting of slopes and phases for n poles at origin and for n zeros at origin. Clear or not? So you finally one point if you want to identify it or not. Now that is nothing but if there are zeros in the transfer function, then the slope is plus 20 dB per decay. And if there are poles in the transfer function, the slope is minus 20 dB per decay. If there are zeros in the transfer function, phase is plus 90 degrees. If there are poles in the transfer function, the phase is minus 90 degrees. Okay. Then you will do a number of poles, a number of zeros, number of repetitions will be the same result you can get in. Okay. So anyway, we'll see all the combinations. Now first you would just take this one. Now this is when the transformation consisting of n zeros at origin and the transformation consisting of n poles at origin. Now we will see if the transfer function consisting of zeros or poles. This is poles at origin and this is zeros at origin. Now g of s, which is equal to 1 plus st. 1 plus st. Okay, this is a 0. Now if you replace s equal to j omega, 1 plus j omega t. If you find magnitude or phase angle, it is completely depends upon frequencies. Therefore, we go for approximations. What type of approximation we are going? Now, when omega t is far greater than 1 and when omega t is far less than 1. When I take omega t is far less than 1, g of j omega, then this is far less than 1, g of j omega equal to 1 plus j0. Therefore, now the magnitude of g of j omega, which is equal to square root of a square plus b square 1, but I want in terms of dB, by magnitude in terms of dB, which is equal to 20 log 1 base 10, which is equal to 0 dB, and the slope is 0 dB per decade, and the slope is 0 dB per decade. Now similarly, when omega t is far greater than 1, now g of j omega, which is equal to, now you neglect 1, 0 plus j omega t, and magnitude, which is nothing but square root of a square plus b square, which is equal to omega t, and magnitude in terms of dB, which is equal to 20 log omega t, means log a plus log b. Now this is magnitude in terms of dB. Then if you measure slope, which is nothing but plus 20 log omega differentiate with log omega, therefore this is 20 plus 0, this is 20 dB per decade finally. Now you just take here magnitude versus frequency. This is magnitude in terms of dB versus frequency. When omega t is less than 1, when omega t is less than 1, the slope is 0 dB per decade. The slope is 0 dB per decade when omega t is less than 1. When omega t is greater than 1, what is the slope? When omega t is greater than 1, slope is rising slope. How much? Plus 20 dB per decade. Now this is when omega t is greater than 1. When omega t is less than 1, slope is 0 dB per decade. When omega t is greater than 1, slope is plus 20 dB per decade. Right? Now this is less than and this is greater than. So when omega t is less than 0 dB per decade, when omega t is greater than 20 dB per decade. But what is the transition frequency? The transition frequency is omega t equal to 1. Omega t equal to 1. Omega equal to 1 by t. This is the frequency, listen carefully, this is the frequency where the slope is changing from one level to another level. This is the frequency where the slope is changing from one level to another level. That particular frequency is called as corner frequency. This particular frequency is called as corner frequency. What is corner frequency? Corner frequency is the frequency where the slope is changing from one level to another level. If there is a corner frequency, this particular zero is called as simple zero. This is called as simple zero, or also called as finite zero. The word simple, the word finite, which means that it is having some corner frequency. 1 plus st form, corner frequency and time constant, is always inversely proportional. You know that. Okay. Now, if this is a simple zero or a finite zero, there exists a corner frequency. Corner frequency is the frequency where the slope changes from one level to another level. Okay. So this is the corner frequency. The slope changes from one level to another level. Now that particular transition frequency is called as corner frequency. Okay. Now this is the simple zero or finite zero. Now the slope and corner frequency. Note down this.